Now, in this time, we're going to be practicing also line structures, but using other atoms different than carbon and hydrogen. So this time, we're going to include oxygen. Say that we have a molecular formula C2H6O. So we start with the molecular formula, and we're going to draw now. This time, I'm going to draw all the atoms, meaning that I'm drawing the Lewis structure, right? So your Lewis structure will be that. Notice that when I have oxygen, an oxygen with zero formal charge, the bonding pattern is like this. So oxygen makes two bonds and has two lone pairs. Carbon, remember, makes 4 bonds. In another bonding pattern that I want you to remember is nitrogen. So similar to ammonia, nitrogen will make 3 bonds and we'll have 1 lone pair when it has 0 formal charge. So keeping that in mind, we're going to be drawing this molecule. So that's one Lewis structure that I can draw using this formula, but I can do another structure. I'm going to make it a bit lower. I can go and do, so I need 2 carbon atoms, right? And an oxygen. And notice these 2 molecules share the same molecular formula. Atoms are connected differently, so these are constitutional isomers, okay? And notice the bonding pattern. I'm going to draw a lone pair so that we keep those in mind, right? Now we go to the line structure. So all I need is, for this one, an oxygen and 2 lines. I know this is a carbon with 3 hydrogens. This is another carbon with 3 hydrogens. And I am done. That will be my line structure. Now for the molecule below, I need a line connecting 2 of the carbon. Then I'm going to draw the oxygen. So this is this line. So let's make it in another color. So the lines that I'm drawing are these and this. So these are the lines drawn here. Now, when you have hydrogens attached to what we call heteroatoms, so different than carbon. So, for example, bonded to oxygen, bonded to nitrogen, sulfur, those are different than carbons. So those hydrogens we are going to draw. So I need to add this to complete the line structure. So this is dimethyl ether and this is ethanol. So in just the molecular structure is important, because also not only we know the shape of these molecules, but it is related to molecular properties. And remember, you learn about, I'm going to draw over here, intermolecular forces before in your previous course. And we know that we have the weakest is the London dispersion forces, also known as van der Waals. Then we have other type of interactions, dipole. And then we have hydrogen bonding. So we learn about those interactions. And so the stronger the interactions are between molecules, the more energy it takes to break those and separate the molecules in going from the liquid to the gas phase. We need to break interactions between molecules. The stronger those forces, we need more energy. So we'll have higher boiling point. And this is reflected right here. So, for example, the boiling point of dimethyl ether is negative 24 Celsius. So this guy is a gas. And now ethanol, however, the boiling point is 78.4. And that is a liquid. So notice, same number of atoms, and notice the huge difference in boiling point. And this is due to intermolecular forces. Between the ethanol molecule is capable of hydrogen bonding. And just to wrap this up, just to show you, remember that again, in using just the line structure, if I do this, one ethanol molecule can be hydrogen bonding, that's another molecule of ethanol, and that could be also hydrogen bonding, yet another. So we have a network, and when we go from the liquid to the gas phase, we need to break those interactions, because remember that in the gas phase, molecules are farther apart. So again, structure has an impact on molecular properties. And we leave it here, and we will continue in the next video.